crazy problems. I'm not going to ask you to maximize the area or something, but they can give you a weird problem and ask you to maximize or minimize it. But related rates is something that's every year on the AP exam. It's because, again, we're applying derivatives to real-life situations, but it's also like throwing in some implicit differentiation at the same time, and it's just super awesome. There was one question a few years ago that I think was like the worst question ever. It was really, really hard. About someone walking towards a light pole and their shadow is changing, and like they're walking at this rate, and so how tall is their shadow after 3 seconds or something? And that's crazy. It was really hard. It was a really hard question. And how tall is the person? And it told you like 6 feet. The person's 6 feet tall, and there's a light pole, and they had to make a similar triangle, and it was out of control. I think so, I don't know. It was weird. You had to make similar triangles and do this whole thing, and afterwards, you're not supposed to talk about the questions afterwards, and afterwards they're like, I'm telling you about this question, and I was like, don't tell me! We all did it now. It's terrible. But anyway, they're not all that bad. But basically, we're going to use a chain rule to find the rate of change of 2 or more related variables that are changing with respect to time. And so we can talk about the rate of a radius changing, or the rate of volume changing, or the rate of someone's height changing, the height of their shadow, kind of weird. I like, this is what your book says, related rates problems are at the heart of Newtonian mechanics. It was essentially to solve such problems that calculus was invented. That's a big deal, kids. It's a big deal today, but it's really on the AP exam is why I think you should learn it. But that's like heartfelt passion right there. That sentence. I did it. Well, it's from the book. I stole it. So I stole passion. All right. So the hard part is these have a lot of geometry formulas. The good thing is on the AP exam, unless it's like area or perimeter of a basic shape, they give you the formula. They don't expect that you memorize how to find the volume of a conical water tank. Who has a conical water tank? That's pretty cool, right? A water tank in the shape of a cone. Why do you need a tank like that? Because it's cool. What are you going to use? What goes in that? I don't know. It's like little cups of water. That's the only thing. This is a water tank. What do you need a tank for that? To find volume of a cylinder, to find volume of anything, you take the area of the base times the height. What would be the area of the base of this cone? That's circumference. Oh. Pi r squared, and then the height we just call h. That is the formula for volume of a cylinder, and a cone is exactly 1/3 of a cylinder, so the volume of a cone is 1/3 pi r squared h. You would never have to know that. They would give you the formula, so don't freak out that part. It is. It's really cool. When I taught geometry, I brought in dry cereal, and we took cones and cylinders of the same radius and height, and we would fill up how many cones did it take to fill the cylinder. No? It's not cool? It's cool. It's an exclusive club. Like, that's what calculus. That's why you take calculus, because you get to be in a club that very few people get to be in. I ordered a math Christmas sweater last night. Like, a math Christmas sweater. Because Facebook knows me, right? It's really creepy that Facebook knows you. And I was scrolling through Facebook, and it said, suggested ad, ugly math Christmas sweater. And I was like, first of all, that's really creepy that Facebook is showing me ads of math Christmas sweaters. And I need to order this. So I did. I did. All right. Here's the new part. I want to take the derivative of this. We want to talk about how the volume is changing with respect to time. So we're going to take the derivative of this with respect to time. There is no time in this problem. Do you agree with that statement? Which means we are going to do implicit differentiation. There is no time, so every time we take the derivative of a letter, we have to multiply by the whatever over dt. Remember doing implicit? Like when we took the derivative of y, we did dy over dx because it was y. So when I take the derivative of b, just 1, but I have to multiply by the rate at which b is changing, dp over dt. constant, can I leave that alone? 1/3 pi. What's the derivative of r squared going to be? 2r, but with respect to time, I have to multiply by dr over dt. Product rule says I'm going to take the derivative of this, and I'm going to leave the h alone. So I'm just going to leave the h here, because r and h are two separate letters, so I have to do the product rule. And I'm going to say plus, again, 1/3 pi is just the constant out front, so I'm going to leave it alone. And now I'm going to leave the r squared alone, and I'm going to take the derivative of h. What would the derivative of h be? Just 1, but I have to do with respect to time dh over dt. And then I'm not actually plugging numbers into this one. I just wanted to kind of show you the process. But the problem would give you some values. They would tell you stuff, which means they would give you enough stuff to plug in, and you would be solving for something. Like they would say, when the rate of volume is changing at this rate, and the height is this, and this is this, find the radius, or find the rate that the radius is changing. So they're going to give you values, and you can plug it in. This one, there's not much to do. I don't even know what we really want to do here. We could simplify a little bit, I guess, right? Could we pull out the 1/3 pi if you wanted to? We could pull a r out. You want to pull r out? Leave the r? I don't know. 1/3 pi r. We could pull out of both of those, just to make it look maybe a little better. And I would be left with 2h dr over dt. Nope, not r. Oh yeah, that's right. Plus 1/3 pi r dh over dt. Anytime they talk about the rate that something's changing, remember that that means the derivative. So if they tell you the rate of the volume, they're telling you this value. If they tell you the rate of the height, right? Rate means derivative. And so that's why you need those in your problem, so you can plug those in and see what's happening. If the rate is a positive value, that means that it's getting bigger, like the volume's growing. If the rate was a negative value, that means that we're losing something. Like in this case, we would be losing volume. How do you feel about that? Do you want me to write that out, like what those letters stand for? Like dV over dt is like the rate that the volume is changing.
Yes.
Rate that volume is changing. dr over dt is the rate that the radius is changing. Changing gets worse each time. And dh over dt is the rate that height is changing. So just like optimization, I have some steps for you. We're going to look at like just a math one, and then we're going to look at some story problem ones. And then that's the whole lesson. So they're not all cones. There's a sphere on your homework. I'm going to give you the volume of a sphere because I think that's the one in your homework that you won't know. But on your test, or even sometimes in the problems in the book, I'll give you the formula. Like you don't have to know them all. But I do have the sphere one listed at the end because I know that you're going to need it. These are my guidelines, and again, helpful things when you're doing something, especially for the first time. But the big thing with related rates problems is they're going to give you some numbers. Don't plug those numbers in until you've taken the derivative. Like you need all in terms of letters first. And so you need to figure out what they give you, what are you looking for, maybe draw a picture if they don't give you one. But here's the big idea. Write an equation involving the variables whose rates of change either are given or to be determined. If we're talking about volume, you write the equation for volume. If they give you a triangle, many times you're going to be writing an equation involving Pythagorean theorem because that's how you can relate all the values. Don't substitute any given values yet, because let's say they gave you the volume in the last problem. and you plugged in 12 because they told you the volume was 12 cubic whatever, when you take the derivative of the value, you just get 0. You lose that dv over dt. So you got to remember, don't substitute in any given values yet. Take the derivative, use the chain rule, implicitly differentiate with respect to time. And once you do that, you're just going to plug in what they give you, and you should be able to solve for what's left. But step 2 is like the big step. Can you write the equation? Can you take the derivative with respect to time? All right, so we're going to start with like a basic one, no really tricky story problem here, just an equation. Then we'll do area one, and then we'll do a crazy baseball one. Okay, go on. This one's like great because you don't have to think about it. They just tell you the function. They tell you let y equals f of x equals x cubed minus 4x. Because y and f of x mean the same thing. If dx over dt equals negative 2 centimeters per second, find dy over dt when x equals negative 3. The good part about this problem is they give me this function, right? I wrote y equals f of x because, just to remind you, they gave me dy over dt. So when I write this equation to take the derivative of it, I'm going to say y equals x cubed minus 4x. So I don't write f prime of x and then get confused. Where does dy over dt come in? And if they're talking about rates of change, that means I need to take the derivative of this function with respect to time. Right? Again, no time in the problem, but I'm taking the derivative with respect to time. So the derivative of y is going to be dy over dt. X cubed is just 3x squared, but I have to multiply by dx over dt. The derivative of negative 4x is just negative 4, but I also have to multiply by dx over dt. Questions on where I'm getting that? I did not plug anything they gave me in yet. Had my function that they gave me, I took the derivative of it. Then you just have to figure out what we're looking for. We're trying to find dy over dt, so you need to see if they gave you everything else that you need. Sometimes they don't. You might have to do a little bit extra work. But in this one, they tell me that dx over dt equals negative 2 centimeters per second. They tell me that x equals negative 3. Having those two values, could I plug those in and figure out what dy over dt is? Yeah. You could simplify if you want, but I'm just going to plug it in. So that would be 3 times negative 3 squared times negative 2 minus 4 times negative 2. Does that become negative 54 plus 8? Did I do that math right? Which is negative 46. A lot of times, not always, they want to talk about the units because we're talking about the rates of change here. And again, this one's kind of weird because it's not really a story problem. But if they tell me that the rate of change of x is in centimeters per second, they don't really tell me all the other values. But I think that the rate of change of y is also going to be in centimeters per second. But we'll look at a story one problem that will make more sense. Just put units on. Let's look at a story problem because that will make more sense than me making up what x and y represent. Okay? Like the next one. This will be better to answer that question. That one was just a silly one, I think. This is a real related problem. The radius of a circle is increasing at a rate of 2 inches per minute. Find the rate of change of the area when r equals 6 inches and r equals 24 inches. Which means they're just giving us two different values to plug in for the radius. Once you have your formula, then you just plug those in. But, first of all, if we're talking about the radius of a circle and they're asking us about the area of a circle, what equation am I going to use that I'm going to take the derivative of? The area equals pi r squared. If we're talking about volume, I'm going to write a volume function. I'm talking about, the triangle, area of a triangle. What do they give me? They tell me that the radius is increasing at a rate of 2 inches per minute. That's not what the radius is, that's how much the radius is growing, right? How much it's getting bigger, it's increasing. So I'm going to say that they're giving me dr over dt is 2 inches per minute. What are they asking me to find? They're asking me to find the rate that the area is changing, which means they don't want the area itself. They want to know if the radius is growing 2 inches per minute, how much is the area changing? So they're giving me, they're asking me to find dA over dt. That's what I mean by like, which quantities do they give you, which quantities are you looking for? If you recognize that rate means you need derivatives, that kind of is the light bulb to say, oh, I need to take the derivative of this. So if I took the derivative of this would just be dA over dt. This is where I feel like you get better at this instead of a prime of doing this when you do related rates problems. Do I need to do the product rule for pi r squared? No, because pi is just a number. So r squared is 2r, so that's just going to be 2 pi r dr over dt. And they asked me to do this twice because depending on what the radius is at that exact moment, the area is going to be changing at a different rate. So that's why they have to give you the values here. It is the circumference. I think it's because, you know, area and circumference and all that is related. I don't think it's coincidental. But notice you do have to multiply by the rate at which it's changing. So you still need to know that. But yes, it is related. That is the circumference is what you end up getting there. So if I was going to do part A here, all I have to do now is plug in the radius that they give me. When the radius is 6 inches and it's changing 2 inches per minute, how much is the area going to be changing by? And you just plug it in. 2 pi times 6 inches times 2 inches per minute. If they ask you for units, I think the best idea is plug in the units that you know, because then you just work the units out. Or, if we're talking about area, you can think about that the units should be square units, since we're talking about area changing, right? But you can plug the units in here and see the answer. I'm just going to leave pi in my answer. You can use decimal if you want. But 2 times 6 times 2 is 24, yes? So I would get 24 pi, and the units would be inches times inches, would be square inches per minute. Because I'm not talking about the actual area is this many square inches. I'm saying that when the radius is 6 inches and it's changing 2 inches per minute, then the area is changing by 24 pi square inches per minute. What does that mean? Let's say you were, let's talk about, I think there's one on your homework that talks about like a balloon inflating, so that's why you use a sphere, and you could argue that a balloon's not a perfect sphere, but whatever. It's, you know, it's a pretend half sometimes. And the same thing with this, like, I don't know, what would be something that could be like the area? You would have to find the radius, which means you'd have to use circumference to find the radius, really. Like, if you really wanted to calculate the... Oh, well, you would have to use a cross-section, which we'll learn next semester how to do. So, like, you could take, like, a little section of what shape you would get there and think about if you rotated it around an axis, how it could make that odd shape, and then we can find the volume of it using integration, which is really cool, because next semester we're going to learn how to find the volume of any shape, even if it's not a geometric shape. And that's where I think calculus is the coolest, because you think, how do they make these weird shapes and know how much stuff it holds? It's calculus. Colin looks like he's going to vomit. But
can you just use water displacement?
I don't know. Maybe. It's not as cool as calculus, Colin. Does that answer your question, Emily, about what this means? It means like how much it's changing by. Right. Let's look at the last one. Have you looked at it yet? I drew a lovely picture of a guy running. No, I mean, I did do it. I made, no I didn't. I made the shape with the shape thing. I drew the line in, found a picture of a guy, put it in. I made it, put it together. A baseball infield has the shape of a square with sides 90 feet long. A player 30 feet from third base is running at a speed of 28 feet per second. At what rate is the player's distance S from home plate changing? You jumped up quickly here, right? Yeah, he's really fast. That's ridiculous.
28 feet per
He's in the majors. He's a super fast guy. He's the leadoff man.
How far is that?
Oh my gosh.
No, I'm not saying that. I'm trying to think.
Feet over 1 second would be what? 5,000? No, that doesn't bottom. 5,280 in 1 mile. 60 seconds in 1 minute. 60 minutes in 1 hour.
I bet it's like 60 seconds.
19 miles an hour.
I don't. No, I don't think.
You guys are the most ridiculous class ever. That you call me out on these numbers. And no one ever in the history of this problem has ever called me out on my 28 feet per second, just so you're aware. How fast I can run? Who?
I think Sam's like 25 feet.
Oh, I don't know if
Pretty
it's
close.
But it's not okay. But there might be a faster person.
We can change it if you want. What do you want to change it to? 8 feet per second? 10 feet per second?
Well, okay. What if he was playing baseball?
He's gonna make turns. He's not. He's gotta slow down.
10. I'm changing it.
It doesn't have to be.
10 feet per second.
No, that's ridiculously slow.
Whatever.
I already took down 28. I'm trying to get it in.
28's okay. It's kind of funny to see how
Yeah.
like
Some kids don't.
We just need to decide before we start labeling stuff here, kids.
28. Yeah.
So we're talking about just the infield, right? Like this is home, first, second, third. So it's a square, 90 feet. So we can say this is 90 feet, right? What letters are we talking about here? The rate that the distance player's S is changing from home plate. That's what we're looking for. So we definitely got to think about an S value at some point, which means we're going to have a DS value, right? Okay, great. DS over DT. Sometimes I just like to list all this stuff out. There's an X in the problem, which means there's going to be an X value and a DX over DT. You might say, why did you plug 90 in there when you told me not to plug things in? I told you not to plug in values I gave you, like in the radius, because the radius can be a different value at different seconds, right? Is that 90 feet ever going to change the distance? Like the distance between here and here is always going to be 90, so that's why you can plug 90 in, because it's never going to change no matter what time you're talking about. Okay, so that's kind of breaking the rule that I told you, but there's no letter you need to plug in there. We're trying to say that as this player is running from third base, how does that even look like I'm not even labeling that right?
He's 30 feet from, so that is 30.
Yeah, so at some point, he's 30 feet from third base. Okay, yeah, sorry. I was thinking he was like running around third base. I'm like, my picture's right there. He's 30 feet here, which means this is the one I don't want you to plug in yet. But we can say over here, we know X is 30. At some point, we're going to plug that in. But at different times, he's going to be different. X is going to be different values, right? Like, so he's going to be getting closer here. And as he gets closer, S is going to be changing too. You agree with that? So we need to write an equation that relates x and s to each other. It works out really nice that this is a square because I could relate these using Pythagorean theorem. Do you agree with that? So I could say x squared plus 90 squared equals s squared. This is where people make mistakes because they plug 30 in for x too soon and they don't take the derivative and then they don't have a dx over dt. And so this is our equation that we're going to take the derivative of. We might need to do some other stuff later, but I'm going to go ahead and take the derivative of it and then we'll figure out what else we need to do. Because I could say that this is 2x dx over dt plus, what's the derivative of 90 squared going to be? Nothing, right? 90 squared is just a number, so it's just 0. So that's just going to equal 2s ds over dt. My s's tend to look like 5s a lot, so sometimes. Or they, yes.
Like, so it's gonna be D something.
Yes, for whatever you use. They use S, and they gave the picture with X, so that's what we're using. But you could use whatever you want, ABC, if they didn't give you a letter. But anytime it's a value that can change, then that's when you use a letter. Because it's over time that those values are going to change. What are we looking for? We're looking at what rate the player's distance S is changing. So do you agree this is the value we're looking for? Which means we should be able to find all the other values either by them giving them to us or by doing some algebra. So they do give me this value, that the player is running from third base at a speed of 98 feet per second,
So is that,
28 feet per second.
so is that dx or?
That is dx over dt, but we got to think about what's happening as he's getting closer to third base. Is that getting smaller or is that getting bigger, that value of x? It's getting smaller, and so that's where you need to put a negative in here. They don't tell me that it's a negative, but because this rate is getting smaller, I'm going to say this is negative 28 feet per second. Here's the good news. You do all this and your answer is the wrong sign. Hopefully they don't give you both choices on a multiple choice test. Then you just are like, oh, it's not supposed to be negative. Or you could think about what should your answer be? If we're talking about at what rate is the distance from home plate changing, should the answer we get be negative or positive? Is this value, as he gets closer to here, is S getting bigger or is S getting smaller? It is getting smaller, which means our rate of S should be negative also. And so that's another way that you can kind of check as you go here. All right, what else do I need? I need to know what S is. So this is where you got to plug 30 in. Not to take my derivative, but the only way I'm going to find what S is when X is 30 is to plug 30 in over here to find S. This is where these problems can get a little crazy sometimes. And I don't want a decimal here, but you don't necessarily have to simplify it all the way out either when you do this. I think you get 9,000 here when you work this out. You get 9,000 equals S squared. So when I take the square root of that, I get S equals the square root of 9,000. Decimal later if you want. You can just leave it as a square root of 9,000 if you want. I simplified it and said, well, that's 900 square root 900 times 10, right? That's 9,000.
90 times 100.
But isn't 900 a perfect square? What are you doing? 900, 90, and 100? You could do that, but then you'd have to break this up as 90 and 10, 9 and 10 still, right? Because you can still pull another perfect square out. See what I'm saying on that? Like, that's okay. And then that would be 10, and then you get 9, 3 times 10. Either way, you get the same thing. Like, this is 30 radical 10. I don't care. Leave it as a square root of 9,000. I don't care. You get a decimal 10. But just don't give me a decimal too early. That's what I want to say. Don't round too early if your answer is going to be a decimal. So finally, after all that work, we can plug in our values. We're trying to find ds over dt, so it's up to you. You can plug all your numbers in and then divide it over, or if you know you're trying to get ds over dt by itself, you could go ahead and say, well, I know it's going to be 2x dx over dt divided by 2s, and you can actually divide the 2's out right away. if you say that looks ridiculous with all those letters, I'd rather just plug it in first and deal with the numbers. That's okay too. But I think we end up with 30 times negative 28. Do you want me to plug all these units in here? Over 30 radical 10. Which means my exact answer is negative 28 over radical 10. And I type that in my calculator, and remember you're supposed to go to 3 decimal places. So you could get an actual value here. Negative 28 divided by the square root of 10. And I got negative 8.854. And I know the rate that that's changing is going to be in the same units that dx was changing, because we're just talking about a triangle here, right? So that would be that it's changing at a rate of negative 8.854 feet per second. I believe there's a question on your homework about a ladder sliding down the side of a house, right? So it's kind of like the same thing. The ladder is the hypotenuse of the triangle, and as the ladder slides down, the x and the y values are changing, and so very similar to this. I'm sure we'll talk about it on Monday, but use this as your guide. This is your homework for 6-day 1. Notice there's only 5 problems. You need to, is this on, did I print this for you? Yeah. Okay, you need these formulas. Surface area of the sphere, volume of the sphere for those first problems. I don't know. They don't know how to fix it. They don't know how to fix it.
We've been coming 2 minutes longer, I think.
Well, we've been starting 2 minutes later, or 2 minutes earlier.
Why does the people can't 808 say?